Hello, everyone. This is Nick Payton here from SigOpt. We're going to give everyone a chance to join, so we'll be getting started in about 2 to 3 minutes. Hold tight. Thanks. Hello, everyone. This is Nick Payton from SigOpt. Thank you for joining our webinar today entitled Tuning 2.0 Advanced Optimization Techniques. I'm joined here today by Scott Clark, our co-founder and CEO. Recently, he gave a talk at a conference in New York called AI for Finance, where he presented a high-level series of lessons for modeling at scale, drawn from our work with a number of leading AI enterprises in the market. And now he's building on that by providing a few additional lessons with more contextual use cases that are more technical in nature. So today we'll be focusing a lot more on specific hyperparameter optimization techniques, particularly advanced techniques within the category of hyperparameter optimization, and how you can apply those to different parts of the machine learning process, as well as anchoring on a few key use cases to demonstrate how this will work in a couple different deep learning instances. So without further ado, I'll hand it off to Scott Clark. If you have any questions throughout the webinar, please ask them directly in the question box in the GoToWebinar control panel that you see, and I'll collect those and be asking Scott each of those questions at the end of the webinar. So be sure to use that question asking capability whenever you need to. If you have any concerns, obviously feel free to raise your hand or go into the chat box, and I'll be monitoring that as well. We look forward to the discussion. Thanks.
Hello, everyone. Thanks so much for joining me today. Really excited to be chatting with you, going over Tuning 2.0, or the advanced optimization techniques. So I started SigOpt about 5 years ago with the dream of accelerating and amplifying the impact that modelers everywhere can have. And what this really means is helping people with domain expertise or context awareness really amplify whatever edge they bring to a problem. And this talk in particular is going to be focusing on kind of the most differentiated models that modelers tend to produce. These are the things where, again, you're applying some secret, some unique data set, some unique context or domain expertise to a problem. And you're not just trying to look for a one-size-fits-all or something that'll get you a answer. You're looking for the best possible results. This is about how do you differentiate yourself from your competitors? How do you provide that maximum value and ROI to your business? And for these differentiated models, whether that's a recommendation engine at a streaming service, a trading strategy at an algorithmic trading firm, a fraud detection system at a credit card company, these things require differentiated modeling. And we're going to be focusing on how we can really make an impact there. So quickly and briefly, how SigOpt works with models, whether they be these more scalable platforms or these extremely differentiated models, is by bolting on top and really allowing experts to confidently experiment with and optimize all of the different decisions and configuration parameters that are inherent in these models. Every single model has tunable parameters, from the simplest random forest where you need to select the number of trees to the most complex deep learning or reinforcement learning algorithm where you're selecting learning rates and feature embeddings and a whole plethora of different configs and magic numbers that actually make these systems work. So SigOpt bolts on top by just seeing what you can tune about the system, suggesting configurations for you to try, which you evaluate however it's built today. So all of the data and all of the training and all of the infrastructure stays on your side. You report back one or more objective metrics. This is how well that system's performed towards your business goals. We learn from that with our ensemble of Bayesian and global optimization techniques to decide the next best thing for you to try, rinse, and repeat. And what this ends up doing is guiding you into that best possible configuration as efficiently as possible. But what I'm going to be talking about today is when it becomes a little bit more complex than this simple setup here, where it's not necessarily just sequential optimization, or maybe when that's extremely time-consuming and expensive to evaluate it, or when you have multiple competing metrics and things like that. But this is the high-level overview of black box configuration optimization and how we help our clients around the world. And we have a lot of experience working with extremely advanced firms, many of which are on the vanguard of AI research. Firms like algorithmic trading and quantitative trading asset managers with a combined $300 billion of assets under management. This includes some of our partners like Two Sigma or Tower Research. We also work with enterprise customers like large global technology consulting firms, streaming services, research-oriented firms like OpenAI. In total, enterprises with a combined $500 billion of total market cap. And what we've learned by helping these extremely advanced AI firms over the last 5 years is that there's many different ways to do modeling, many different values you can get out of this, but there's different ways that you can apply your expertise or specific tools to really make sure that you get that edge. And these are companies that are about having that edge, maintaining that edge, and have been able to do it sometimes over the course of decades. So I'll start out by showing an extremely simplified version of a machine learning kind of workflow. There's obviously many different versions of this at varying levels of complexity out there, but I'll use this as kind of a way to phrase some of the things that we'll be talking about today. So it can go from defining what success means all the way through ETL and model selection, through training, tuning, and eventually deployment. And one thing that I'd like to point out is good experimentation and optimization is key to all of these different steps. It's not just a last mile problem where maybe you're doing hyperparameter optimization over kind of more traditional learning rates, number of trees, stochastic gradient descent parameters, etc. But it can also exist throughout the rest of the process as well, whether that's in the training itself, making sure that you're maximally utilizing resources by doing things like early stopping and convergence monitoring. It can help in the model selection process as well by doing things like intelligent neural architecture search, or just search over different completely orthogonal types of modeling approaches. It can help in the data engineering and feature engineering component. Many times when people are dealing with more complex data sets, whether they be text, video, images, speech, there's many different ways to do embeddings of this data. There's many different ways to do feature engineering. A lot of times those features themselves have tunable parameters. So ETL itself isn't necessarily a very static or kind of one-shot approach to doing data transformations, but it is something that can be tuned itself. Finally, defining metrics. We put this at the very beginning of the process here because we firmly believe the only way you can be successful is by being able to measure that success very early, being able to say, what does it mean to have a better model? What does it mean to be able to beat the status quo? What does it mean to be able to say that I successfully was able to amplify the business's outcomes. And we talk about ways that you can do optimization when you might not know ahead of time exactly what trade-offs you want to make, but you have an idea of what levers largely move the business itself. And finally, retuning becomes incredibly important. When you're not just doing modeling in order to get one right answer and then moving on to the next thing, but it's really about how do you make sure that you stay on top of a potentially adversarial environment like algorithmic trading or fraud or some of the work we do with the US intelligence community? How do you make sure that you're really staying on top of not this static mountain, but really surfing a wave and staying abreast of the changing environment underneath you as the models, data, or potentially metrics themselves shift? And obviously, you can get a lot of value from thinking about this from an end-to-end approach, really trying to tune the entire system together, from the metric definitions to the feature engineering to the model selection to the hyperparameters and retuning that continuously. But what I'm going to be really focusing on today is three key parts. And they really allow for a large amount of benefit to both you as the user and the business as a whole. By having optimal experimentation, by having a single place where you can easily learn from, reproduce, and start kind of already running on problems, this allows you to learn fast and fail fast. It allows you to be able to say things like, I tried deep learning on this problem, and I'm pretty sure it doesn't work for my problem, not because I didn't configure it properly, but because it isn't actually the right technique for this problem, versus kind of always wondering, oh, what if I had done just one more different architecture or one more different hyperparameter configuration? This also allows you to not get stuck in local optima in this larger modeling space, where maybe an untuned random forest beats an untuned, more sophisticated method, but you don't realize that by properly tuning them, that ordering may shift, and you end up spending lots of time and energy perfecting that suboptimal model, not realizing that you're leaving a ton of value on the table completely unaware. This also allows you to start connecting outputs to outcomes. In academia, it's great to just show that you can make an epsilon improvement on a log loss or an error rate or something like that. It's about squeezing as much as you can out of academic metrics. But more often in industry, what we find is it's about making real business outcomes. And instead of just tuning for some of the traditional academic metrics where there might be nice asymptotic properties, nice ways to show proofs and things like that, by looking at things more holistically and saying, how do I create a set of metrics that might be a little bit more complex, but are much more correlated to what I'm actually trying to drive for the business? By doing experimentation and optimization with that frame of reference and that in mind, really allows you to produce as much value as possible for your individual companies. And finally, it's about boosting productivity. And this is really about you as experts not wasting your time doing things like 10-dimensional optimization in your head, not spending years gaining intuition about a very specific architecture only to have the state-of-the-art shift and have all of that intuition become worthless. This is about allowing you to confidently and reproducibly optimize your models and focus on where you can actually provide an edge or a difference to your business and your customers. So as I mentioned, we're going to be focusing on three specific components here of the modeling stack. These can obviously be interchanged or coupled together, or think of more holistically, as I mentioned before. But I'll be talking about when you're doing metric definition, how to think about balancing potentially competing objectives in order to get to the best business result, even if you don't know ahead of time what that exact trade-off you want of specific underlying metrics are. I'll be talking about model search and model selection, particularly around tuning the architecture of neural networks, often called neural architecture search. I'll also be talking about when you're doing more traditional hyperparameter optimization, but a lot of the standard techniques might not scale for some of your more complex problems. When you have long training cycles that might take hours or days, and sequential traditional optimization techniques might completely fail. How do you kind of harness information about the system as you're tuning it in order to more efficiently get to that best possible result, where it would otherwise be intractable? So these techniques, again, largely are metric definition, model search, and long training cycles. Each one of these that I'll be presenting today has a blog post associated with it that goes into a lot more technical depth. Each of those blog posts also have code available on GitHub for reproducing this and modifying this for your needs. And quite a bit of research as well developed by our full-time research team at conferences like NeurIPS and ICML, et cetera. So a lot of these references will be at the bottom of the slides, and they'll be at the end as well, and we'll make sure that everybody gets a copy of this deck. So first up, metric definition with multimetric optimization. As I mentioned before, the very first part of doing a modeling task is often defining what success even means. How do we know whether or not that new feature or that new model or that new data set or whatever it is actually made a difference if we don't have a measuring stick that we can trust? The problem with this is, unlike in academia where there might be a previous paper that you're trying to beat or something like that, oftentimes in the real world, there's these noisy, complex objectives that you're trying to shoot for. You might want the most accurate model, but it might be an IoT use case, so it needs to be fast. You might want a model in an algorithmic trading setting that has the highest Sharpe ratio or the highest ability to make a profit, but you also need it to be able to trade enough money to be able to make a significant actual bottom line difference. And trading these things off might be very difficult because you might not know ahead of time exactly how different configurations of that model affect these competing objectives. So multimetric optimization is a way to say, instead of forcing you to make that decision up front, let's optimize these models to give you this efficient Pareto frontier, this efficient trade-off between these individual metrics that you as an expert can then go back to and select from after the fact. So then you can make intelligent trade-offs between how you want to maybe decrease accuracy in order to vastly increase training time, for example, or decrease training time, for example. And this can be extremely powerful, again, as you're doing that metric selection process throughout the actual modeling process as a whole. And there's a bunch of these different applications, again, between balancing competing objectives, and we have some examples of this, helping define and select these metrics and how they interact with the individual configuration spaces you're tuning, to being able to set things like setting hard thresholds of, I care about accuracy, but after a certain point, it's diminishing returns, or I care about training time, but beyond a certain point, it won't fit on my machine. There's lots of different ways that you can add kind of your expert contextual knowledge to this problem as well to really guide this search to be exactly what you want it to be. So I'm going to go through a brief example here. This was some joint work that we did with NVIDIA. All of this is available on their blog, linked here, and there's also code available on our GitHub examples. What I'll be doing is just walking through the first use case very briefly here. This was doing a time series sequence classification problem using convolutional neural networks. And really the goal here was, how do we kind of trade off complexity with accuracy? So a more complex CNN has a higher inference time, but it could also have higher accuracy. Whereas the simple one has lower accuracy, but potentially lower inference time. And this is particularly relevant for our customers that are doing work on embedded devices, whether that be cell phones, whether that be IoT applications, where they want to be able to make this trade-off as intelligently as possible. So we are going to be trading off, again, inference time and accuracy, and comparing various methods on the SigOpt platform both our proprietary ensemble of Bayesian and global optimization techniques, as well as a more standard kind of random search with many more suggestions. We're going to be tuning a variety of things here. Again, this kind of goes to show that sometimes opening up the space of what you would configure can have pretty meaningful results. Here we'll be doing both neural architecture search as well as traditional hyperparameter optimization jointly. And what we see here is when trying to make this trade-off between inference time and validation accuracy, different methods produce different frontiers or different trade-offs. On the left here, we have random search, just kind of blindly trying configurations. This is akin to trying to climb a mountain by jumping out of an airplane and just hoping you land at the peak, versus the proprietary ensemble behind SigOpt really focusing in on this Pareto frontier, really pushing it out as far as possible so you can make these trade-offs as intelligently as possible. So what you're seeing here is 10 times fewer total training runs, 10 times less wall clock time, but ultimately a large majority of the combined Pareto frontier being found. And from a business perspective, what this means is instead of getting one answer or one configuration that you'll check into Git and let run, what you're getting is this set that you can then, as an expert, say, maybe I want to just maximize accuracy, or maybe I just want to minimize inference time as much as possible. But potentially, there's these Goldilocks points where you can have the best of both worlds. You can say, I'm willing to give up 1 point in accuracy in order to have a 3x speed up in inference time. But this is the type of trade-off that you might not be able to make ahead of time if you were forced to normalize these against each other and not even realize what's feasible upon that Pareto frontier. So in this next section, I'm going to be talking about kind of extending this. I already gave kind of a hint at this before of doing neural architecture search in the previous previous example, but I'm going to be extending upon that to when you're doing more complex architecture searches. Often there's a hierarchical or conditional dependence between parameters. Specifically, when you're selecting things like which stochastic gradient descent optimizer am I going to be using? Different ones from Atom to Atagrad to gradient descent momentum, etc., have different underlying sub-hyperparameters. Some of them have decay rates, some of them have momentums, learning rates, etc., but not all of them affect all of the others equally or at all. So by creating a conditional or hierarchical parameter space, we're able to, as efficiently as possible, search through these non-overlapping choices. In this example, I'm going to be walking through another piece of joint work that we've done with NVIDIA. This one was optimizing end-to-end memory networks. It was a great paper by Facebook AI Research around question answering using memory networks. Basically, being able to ask the model, give the model specific pieces of information, like Mary moved to the bathroom, John went into the hallway, and then asking it a very specific question where it might have to apply logic, where it might have to corroborate information, etc., to get to a specific answer. So obviously, there's a lot of work that goes into phrasing this problem, building the network, etc. But what we're showing here is by tuning it effectively, you can get boosted performance beyond everything that you as a domain expert apply to that. So again, this is performance that would otherwise be left on the table and is completely additive with what you're bringing to bear to the problem. In this specific example, again, we compare against kind of the baseline from the paper itself, which was tuned by the experts before it went into peer review and was eventually published. We also compared it against standard techniques from the academic literature, like a randomized search. one randomized search with the exact same number of observations as the SigOpt ensemble method, and one with 20 times as many observations. And what we see is even when running this independently many times, we see consistently that techniques like the ensemble approach outperform more brute force approaches. Furthermore, when you start to break this down to not only which method was able to get to the best overall accuracy, but you start to think about what was the compute and time costs associated with getting to that accuracy, you can see that these more intelligent methods start to really separate themselves. So not only is this about getting the best result, but it's about getting the best result in as little wall clock time and with as little compute time as possible. And in this case, the ensemble was almost 20 times as efficient as that more brute force approach that's often advocated in the literature. What this means for you is, as you're starting to think about tuning your most sophisticated models, again, breaking outside the previous constraints that you might have had in terms of how you phrase that problem to, again, capture as much value as possible. My final example here will be around long training cycles and leveraging a technique from the academic literature called multitask optimization, and specifically doing that in parallel. So the intuition here is when you're dealing with a really large deep learning system, reinforcement learning system, algorithmic trading strategy, whatever it may be, sometimes it can take a really long time to see how a specific configuration has performed. So maybe it takes hours, days, maybe it takes a large cluster in order to even compute the result of a single solution. So the intuition between multitask optimization is maybe we can get cheaper, noisier information by subsampling, or maybe by only letting it run for a certain number of epochs, or maybe changing the granularity of the simulation itself. And the goal here is to leverage that cheaper, lower fidelity information in order to only sample the full cost expensive model as infrequently as possible. So there's a handful of papers here that have become very popular in the literature in the last year or so. You can think of this as a much more intelligent designed approach to adaptive experimentation compared to some of the random search variants like Hyperband or whatever it may be that still just use random search, and early, this is about deciding exactly what to sample, when, how much, and be as efficient as possible with those resources. And I recommend reading these papers. They're really good. They kind of explain this, the intuition quite a bit more. But again, the idea is by sampling a task with a much smaller amount of total data, we can get a rough cut of what's interesting and then leverage more expensive tasks to really zoom in on that interesting area and as efficiently as possible get to an optimum. Another thing that we can leverage here is the full parallelization of an ensembled Bayesian optimization approach. One nice thing about about naive methods like random search or Hyperband is a kind of embarrassingly parallel. Because they're not learning anything, they can just do everything completely independently. The cost of not learning anything is inefficiency, but it can be really great if you have effectively infinite compute. But by having this ensembled server-like model with a system like SigOpt, this allows us to do that parallelization, to do that resource scheduling, to be able to asynchronously parallelize these individual evaluations independently up to 100 different independent evaluations per experiment, which allows us to kind of multiplicatively get the benefit from something like multitask, as well as leverage a larger compute infrastructure. This example that I'll go over briefly here is based off of a blog post by Meghna, an engineer here at SigOpt who has done some great work for us and goes into quite a bit more detail on this, as well as providing code examples on our GitHub page. She'll also be speaking about some of this at MLConf in San Francisco coming up here soon. What we're going to be doing, though, is kind of a classic computer vision problem, image classification. In this case, it's multi-class image classification. We're going to be taking the Stanford cars data set. That is about 16,000 images of cars. And we're going to try to train ResNet, in this example, to identify the car, the make, and the year for each one of these images. So obviously, there's been lots written about ResNet at a super high level. It takes an input image, and then it goes through some number of convolutional layers, ultimately coming up with a classification for that eventual output based off of what it's learned throughout training. And I'll reference the paper here, and obviously there's been a lot written about this, so I highly recommend reading it if you haven't. In this specific example, though, what we're going to be looking at is various ways that you can tune ResNet. You could do maybe an architecture comparison where you're looking at maybe ResNet 50 versus ResNet 18, kind of a larger, more heavy-handed variant of the method versus a smaller architecture. You can also compare whether or not full fine-tuning is better versus only tuning that kind of final fully connected layer. And we'll compare these different scenarios against both the baseline from kind of just taking the default hyperparameters out of the classic paper versus doing something like multitask versus traditional Bayesian optimization versus, again, a more naive approach like hyperband or random search. So again, just visually, which I think explains this a little bit better, we're going to both be doing in one set fine-tuning, so changing the hyperparameters of the larger system and allowing it to retune the full weights of all of the convolutional layers as well as the fully connected layer. And then in the other scenario, we're only going to be retuning the fully connected layer after updating the hyperparameters. And we're going to be looking at kind of some of the classic parameters that you need to tune with this system, from learning rates to a scheduler that was proposed in the paper to things like momentum and weight decay. And what we see here is actually a really surprising result. It was surprising to a lot of us here. One was the result is that taking the simpler, smaller network and doing fine tuning produced significantly better results than taking the ResNet 50, the larger architecture, and only doing tuning on that fully connected layer. Both of these networks were pre-trained with ImageNet, so we assumed that transfer learning would allow us to get similar information about the ResNet 50 setup. But in reality, even though it was both multi-class image classification tasks, by fine-tuning, not only were we able to get better results in the baseline, but there was a bigger delta to be had by doing hyperparameter optimization as well. What this means for you as an expert is don't necessarily assume that transfer learning is going to work for your system. You should look into doing kind of more fine-grained tuning as you're doing it. And also, as you open up kind of the ability for these hyperparameters to influence the underlying problem, the delta you can get over baseline can be pretty significant as well. And it's just worth noting again that all of this is in addition to any feature engineering, any domain expertise you're applying to the problem, anything that you're doing that can really differentiate you from your competitors. This is the value increase in the metric that you get from doing this hyperparameter optimization, and is additive with all of the work that you're doing here. And again, really the intuition behind this, and there's the blog post that I'll point you towards, and also an NVIDIA GTC talk that I gave a while back that's up on YouTube that goes into more detail. But what the real intuition here is, by sampling certain parts of the space with smaller, cheaper tasks, we're able to only utilize those expensive tasks where it really matters. Only when we're really zooming in on, in this case, the region of the learning rate space that we think has the most possible utility. And this is being done, of course, across all of the different dimensions simultaneously, but it's really about not wasting resources where you know there isn't going to be a great result, like a naive method might, and learning from that to not go back and resample like a naive method might. And again, further amplifying this with things like parallelization. So instead of paying not only what the pure sequential cost would be to tuning this, but breaking that up into smaller subtasks, and then taking those smaller subtasks and parallelizing them independently, so each machine is doing a different task with a different configuration, you can bring the wall clock time down from something that would otherwise be potentially intractable to something that can run over the weekend. And the reason why this is important is by really, again, getting the most bang for your buck. How do you get the most improvement per dollar? And in this case, doing that full fine tuning can really make that big difference. And by using a more intelligent solution, you can really bring this down as well. So in this case, we were comparing multitask, which I've shown you here, to Bayesian, traditional sequential Bayesian optimization, to a more randomized search similar to Hyperband. And what we were able to say is, while certain things like these naive methods can be embarrassingly parallel, in practice, you're often limited by the size of your cluster. And when you think about it in terms of which was able to get to the best result in the fastest wall clock time or the least amount of money, the results speak for themselves. So again, today I went over 3 different techniques, 3 different ways that you can think about this problem beyond maybe the traditional way of thinking about experimentation and optimization, about defining your metrics either upfront or allowing yourselves to really explore that metric set, that metric space while you're optimizing. I talked a little bit about how you can do model selection, whether that's neural architecture search, or whether that's having these hierarchical parameters to really expand the breadth of what you can tune about your system and sometimes squeeze even more performance out of them. And then I also talked a little bit about how long training cycles don't need to be the reason why you don't optimize. There's solutions out there that allow you to adapt these problems and still be able to have your cake and eat it too. Use the most sophisticated long-running method that you want, but make sure that you're getting the most out of it, and doing so with the fastest wall clock time and compute efficiency. So before I pass it off to Nick for some questions, just wanted to point out that if you're interested in trying our solution, we'd love to get in contact. Just go to sigopt.com/try-it. I'd also highly recommend the ebook that we help sponsor by Sam Charrington of This Week in Machine Learning. In it, he talks about machine learning platforms, kind of going through different use cases from some of the leading AI firms, but then breaking it down into chunks so you can think about how to build up your best AI platform for your business itself. We'll also be at a couple of conferences coming up here in San Francisco, both the AI Summit in September, and then TWIMLCon, again hosted by Sam Charrington of This Week in Machine Learning in early October as well. So we'd love to see you there and love to dive deeper.
Thanks, Scott. Thank you for the presentation and for providing a lot of those use cases. Just to confirm what Scott said earlier during his presentation, for anyone who is interested in sharing this information with your colleagues, we are recording this session. We will be posting a video of that recording on our YouTube channel, which I highly recommend you follow, as well as providing the slides through SlideShare. And we'll be making both of those available through a direct email to you all after this webinar. Before we head off, though, there were a couple questions that came up that we didn't get a chance to answer during the presentation outside of those logistics. The first question related more specifically to SigOpt and the way that our hyperparameter optimization solution works. Particularly, the question was around whether we actually host the training of the models on our own platform.
Great question. So I know I went over this briefly at the beginning, so I'll just jump right back over to this diagram. The goal of SigOpt is not to replace the work that you've already done, but really just to bolt on top and supercharge what the work that you've already applied. So in this setting, we're a software as a service solution that with a simple REST API interacts with your model only at that configuration layer. So you define what you can tune about the system, all the different configuration parameters, hyperparameters, architecture parameters, feature embedding parameters, basically anything you can tune, any magic number that would sit in a config file. That's a single API request to tell us what we can tune, another one for us to give you one or more suggestions to try. You evaluate that, and all of the training happens on your system. All of the evaluation of the model happens on your system. So no proprietary data or IP of the model is passed to us, only how well that configuration performed, whether that's a single metric like accuracy or multiple metrics like I went over earlier. Then this process repeats, but this simple kind of ask-tell server model means you're always utilizing your resources fully, and we can do some of that kind of distribution of resource management for you in the parallel case, but also none of your IP is coming to us. Only the best results are coming back.
Great, thanks, Scott. Another question came up related to the use cases that you went over. This person is asking, given the fact that we went through deep learning only use cases, is deep learning the only real application for our product? Great
question. So quick answer is no. We work with people in a wide variety of different spaces, from more traditional machine learning, which is especially prevalent in regulated markets. These are people using SigOpt to tune things like random forests, gradient boosted machines, larger kind of ensembles of these more explainable models. We do a lot of work with deep learning, as I've shown here, but we also work with people with proprietary trading strategies, or like our friends at OpenAI who use us for more reinforcement learning techniques. Basically, if it's a model that has tunable parameters and you have a measurement for success, then we can bolt on top and help you tune it. And we've done that with businesses around the world.
Awesome, thanks. And then this is a little bit more technical. There's a question around the way multitask optimization works. I think what they're getting at is how it relates, because you mentioned hyperband, how it relates to hyperband and early termination, how they should think about it in that context.
Yeah, great question. So for a system that's kind of just extending one of the naive brute force methods like hyperband, the goal there is to try random things, and then if the random things look bad, then stop investing resources in them. And this can be really handy if you can make some strong assumptions about the space, or if that kind of random search is good enough for your problem. The difference between that and something like multitask optimization is, instead of just trying everything and culling the weak ones, like an evolutionary search algorithm would do or something like that, what we're doing is very intentionally selecting not only what we should try, but how far we should go with it ahead of time. And this allows us to do much more efficient resource allocation, much more efficient scheduling, and ultimately produces better results, better global optima, because we're learning from previous techniques, but also get there in faster wall clock time and fewer total compute cycles as well.
Awesome. Thanks, Scott, for that. The last question we have relates to really specific types of use cases. And the question is, what sort of financial use cases do you have, and do you have specific examples related to default rates and mortgages?
Yeah, so we have a whole bunch of different use cases on our blog, or in the 20+ papers we've published at different conferences like NeurIPS and ICML. If you have specific use cases, we'd love to get on the phone with you, to be honest, and kind of make sure that we fully understand your unique problem. We're big proponents to you knowing more about your problem and your model than anyone else in the world, and we just want to help enable you to experiment and optimize as efficiently as possible. So we'd love to learn more about your specific use case and then brainstorm with you on how you can make sure you're not leaving any business value on the table.
Great. I'll make sure that we also do more specific follow-up on that particular question, because I know you're looking for a little bit more detailed information on the methodology related to default rates and mortgages. So thanks for that. Okay, I think that's all we have actually. So Scott, thanks for your time today. And thank you everyone for attending the webinar. We'll be following up shortly with the slides as well as the recording. Join us for the next one. We'll be doing these more regularly going forward. Thank you.
Thanks everyone.